roots. Okay? So let's start right here, in which we can start. Let's first of all talk about cube roots and see what we can say. All right? Now, just as from the theorems that we have been developing today and from the ideas that we have been looking at with respect to square roots, let's look at something such as this. And if I put a little 3 up here to indicate this index number, we refer to this as the cube root of 8. Is that right? So the cube root of 8 must be equal to some number. And what number is that, Ken?
2.
In this case, it's that number 2, such that this number 2 cubed is equal to 8. Is that right? Isn't that what we mean by the cube root of 8? All right. Now, let's look at the cube root of negative 8. And what do you think we may say about the cube root of negative 8? And Steve?
Negative 2.
Is equal to negative 2 because negative 2 cubed is equal to negative 8. Is that right? Okay. And now, do you think this is true? What do you think we might say about, well, say the cube root of A? All right, and the cube root of A cubed is equal to what? Is equal to A. And is this true for every real number A, for every A in the set of real numbers? All right, suppose A, in this case A happens to be negative. Is that right? So it's equal to whatever this number A is. Is that right? And if A is positive, as we have it here, it's still equal to the number A. So in fact, this is what we mean by the definition. This is our definition of the cube root of some number A. It's that number which when cubed is A itself. Okay? And I think this carries through immediately from what we mean by the square root of a number, except for square roots, we have to be careful about what kind of number A we can have in here. Okay? Let's look at a few other ideas that have to do with cube roots. And suppose we were to take a situation, suppose we had the cube root of 8 times 27. Now, on the basis of what we said about square root, do you think that this is equal to the cube root of 8 times the cube root of 27? Do you think we may say that? Would you all accept this idea? All right. And now, of course, you know that the cube root of 8 is what number? 2. And the cube root of 27 is 3, right? Because 3 times 3 times 3 is 27. And, of course, 2 times 3 is 6, all right? Now, in fact, I think we can generalize this in the form of a theorem in which I think we can say for every A and B belonging to the set of real numbers, okay, what now do you think we might say? The cube root of A times B is equal to, and who would like to write our conclusion here? What is our statement going to be? Ken?
Cube root of A times cube root.
The cube root of A times the cube root of B, okay? And this is very much like a product property that we have seen in today's and yesterday's lesson. So in fact, let's give this a name of a product property of what? Of cube roots, okay? A product property of cube roots that we may look at from this theorem. I'd rather not prove it, but simply go on and look at some other ideas. Do you think we can talk about the cube root of 8 divided by 27? And what do you think we may say about this? And do you think we might say, Chip?
The cube root of 8.
The cube root of 8 all divided by
the cube root of 27.
The cube root of 27. And of course the cube root of 8 is 2 and the cube root of 27 is 3. All right? And do you think we may say this for every real number A and B, except for this number here cannot be 0? Is that right? In fact, let's indicate that as a theorem in which we may say, what? For every A, let me call it the number C, belonging to the set of real numbers, where C cannot be equal to 0, where this number here cannot be equal to 0, the cube root of A divided by C is going to be equal to, and Ken says?
Cube root of A over the cube root
The cube root of A divided by the cube root of C. Okay? All right? And I think we may use this idea as we look at a number of examples. In fact, let's do that right now and see if we can't look at a few numerical cases. And suppose I were to take a situation such as the cube root of 0.008, okay? And now I want that number, which when multiplied by itself 3 times, is equal to 0.008. So what number do we have here which will do this for us? Ron?
0.2.
Is equal to 0.2. Does everyone agree with that? Okay? Because 0.2 times 0.2 is 0.04 times another 0.2 is 0.008. Is that right? Okay? And I think that you will agree that this statement is correct. Now, let's look at another example. Suppose we had something such as the cube root of 54a to the 7th power, okay? And now let's see how we may write this. Now, we're looking for perfect cubes, aren't we? So you look at the number 54 and you ask yourself, does that contain a perfect cube? And does anyone see a perfect cube in there? Steve?
4.
4, well, let's now, I'm thinking of the number 54, and I don't think that 4 is a perfect cube to begin with. And does 4 divide 54? Nor does 4 divide 54. So, Todd?
27.
27, all right? So if we thought of this, let me break this up into the form of their perfect cubes first. 54 is what? 27 times 2 times, now let's look at a to the 7th power, and how may we write that? How would you like to write that, David?
A cubed times A cubed times A.
All right, and now instead of writing it as a cubed times a cubed, what's another name that we may write here, Steve?
A to the 6th.
A to the 6th power times a, okay? Now I'm indicating these in this step here, but I hope you get into the habit of being able to do that in your head. Now, the cube root of 27, let's use our theorem, is what?
3.
Is 3 times, now here we still have the cube root of 2, which we can't do much with. The cube root of a to the 6th power is what? Is a squared. I want that number, which when multiplied by itself 3 times is a to the 6th. So a squared times a squared times a squared is a to the 6th. Is that right? All right, now whatever is left is what? The cube root of, and what do we have under the radical? We have what? 2 times a, okay? And notice now we do not have to put any restriction on a here. Okay, so here we finally have then 3a squared times the cube root of 2a as the most simple name for this expression right here. Okay? Let's look at a third example and see what that might be. Well, how about something such as the cube root of 4/9? All right? Now let's use our theorem in which we have here the cube root of 4 divided by the cube root of 9. Now, is the cube root of 9, is 9 a perfect cube? No. So we now would like to have a perfect cube downstairs here, and the cube root of 9 times the cube root of what number will give us a perfect cube? Ron?
Cube root of 3.
Times the cube root of 3. So what's another name for the number 1 that we might use here? Ron?
Cube root of 3 over cube root of 3.
Very good. The cube root of 3 divided by the cube root of 3. Is that right? Okay? Because now we have here in the denominator the cube root of 9 times the cube root of 3, which is the cube root of 3 cubed. Let me think of it as 3 cubed. And of course the cube root of 3 cubed is 3. Now whatever is in the numerator is left, in which we have the cube root of 4 times the cube root of 3 is what? The cube root of 12, using our theorem. Okay? So this then is the most simple name for this expression here. All right? Well, let's go on and look at the other idea that we'd like to do today, and that has to do with the nth root, okay? So let me call this idea B, in which we're talking about nth roots. Now, let's see what the best way for us to proceed is. Well, suppose we had, say, the 5th root of 32. All right, now I want that number, which when multiplied by itself 5 times is 32. So the 5th root of 32 is equal to, and Todd, is equal to 2 because 2 to the 5th power is 32. Is that right? Okay. Now suppose we had the 5th root of negative 32. And what now do you think we might say about this, Todd?
Negative.
Is equal to that number, negative 2, because negative 2 to the 5th power is equal to negative 32. Is that right? Now notice here this number a, if we thought of this as a, happens to be positive, and here a happens to be negative. And notice here we're taking an odd power, an odd root. Is that right? An odd root. So what do you think we might say? If n is odd, okay, if this number n here is odd, all right, then what can we say? Then for every real number a, okay, the nth root of a is what kind of a number? What can we say about the nth root of a? Certainly it's going to be what kind of a number. Is this well defined is the question, Ken?
A real number.
This is going to belong to the set of real numbers, okay? Let's first of all establish this conclusion. Notice here we have a 5th root of 32. This is an nth root, which is an odd number, a positive number, and the nth root of an odd root of a negative number, and both of these are well defined, okay? These are real numbers. And here we have that generalization. If n is odd, then for every real number a, the nth root of a is also a real number. In other words, it's well defined, okay? Now, as opposed to a situation, suppose we were to consider the fourth root of 16. Well, all right, what then do we know about the fourth root of 16? And what number is this equal to, Chuck?
2.
This is equal to that number 2 because 2 to the fourth power is equal to 16. Is that right? Okay. Now, suppose we were to consider the fourth root of negative 16. And you say to yourself, well, I want it to be some number x such that this number x raised to the fourth power is equal to negative 16. And what's your conclusion about x to the fourth power is equal to negative 16? Do you have some real number there, Steve?
X is not a real number.
X is not a real number. So therefore, I think our conclusion is that the fourth root of negative 16 does not belong to the set of real numbers. Is that right? It is not a real number. So let's see if we can't generalize this idea. If n is even, all right, if n is an even number, and what? A is greater than or equal to 0, all right, then what is our conclusion about the nth root of a? What can we say about the nth root of a? What kind of a number is that? Is this a well-defined number? And what can we say?
It's a real number.
This certainly is a real number, okay? All right, such as we have here. The sixth root of 38. Is that a well-defined number? Even though you can't find out what value it is it a well-defined number? All right, how about the 18th root of the square root of 1,000? Is that a well-defined number? Okay. Now, suppose we were to ask ourselves if n is what? Is still even, and a is what kind of a number? If a is less than 0, then what is our conclusion about the nth root of a? What now must we say about this number? And here's a case where what? It does not belong to the set of real numbers, okay? In other words, this number, when n is even and a is less than 0, this is not a well-defined number, okay? It's not a real number. Now, from that, I think then we can say something about the, well, in fact, let's make the definition of what is meant by this. If the nth root of a, okay, is indeed a real number, if it's well-defined, in other words, then our definition tells us that the nth root of a all to the nth power must be equal to what number? Must be equal to a, okay? This is exactly what we mean by the nth root of a. It's that number, all right? It's that number which when raised to the nth power is equal to a, okay? And this is the generalization of this statement right here. Well, let's see if we can look at one or two properties of these numbers. And in fact, I think we can generalize from what we have already said in terms of a theorem. And let's see how the best way for us to say this theorem is. Well, suppose we had for every a and b and c belonging to the set of real numbers where c is not 0, okay? And if, let's indicate it this way, if the nth root of a and the nth root of b and the nth root of c are all well defined, okay? If indeed they belong to the set of real numbers, then what is our conclusion? Well, in fact, I think we may say two statements. What then can we say about the nth root of a times b? This is the same theorem that we had for square root, and now in this lesson for cube roots, and now we're trying to generalize it to the nth root, and Chuck says
It's equal to the nth root of a
the nth root of a
times the nth root of b.
times the nth root of d, okay? And then the other conclusion that I think we would like to make is what? That the nth root of a divided by c is equal to, and Sally?
The nth root of a.
The nth root of a
Divided by the nth root of c.
divided by the nth root of c, okay? And in fact, if we had to give this a name, well, let's just call this properties of nth roots, okay? Properties of nth roots. We could call it a product property and a quotient property for nth roots, okay? Let's look at a few numerical examples of an nth root and see what that looks like, okay? Suppose we had something such as, the fourth root of, and let me just make up some expression here, 16, x to the fifth power, y to the fourth power. divided by 27z cubed. Okay? A rather messy looking expression in which we now would like to come up with the most simple name for this. Well, let's take it one step at a time, all right? Here now is the fourth root of something. Let's use our theorem. Now, let's think of this number 16. Is that a perfect fourth root? Yes. All right, let's just keep that in there as simply the number 16. And let's think now of x to the fifth power, and writing that with a perfect fourth root in there is what? X to the fifth we may think of as, Chip?
X to the fourth times x to the first.
X to the fourth times x, and we still have up there what? Y to the fourth power. Is that right? And now let's use our theorem, in which this is divided by the fourth root of, and here we have 27z cubed. Okay? Now let's work vertically here. Let's actually try to simplify our numerator as much as we can first. Okay? Now the fourth root of 16 is 2. The fourth root of x to the fourth power is x. The fourth root of y to the fourth power is y. And now whatever is left is still the fourth root. Is that right? So what now is left under the radical? And we have there what? X, simply x. Is that right? Now in the denominator we have the fourth root of 27z cubed. Now, is 27 a fourth root? No. Now, but 27 is what number? What do you know about 27? It's what? It's 3 cubed. So if you say to yourself, if I had a 3 to the fourth power there, the fourth root of 3 to the fourth is well defined. Is that right? Indeed, that is a perfect fourth root. So what's another name for the number 1 here that you think you might want to multiply by? All right, now here you also have to worry about the fourth root of z cubed. And Brenda says
3z over 3z.
times, let's see now, another name for the number 1 is what?
Oh, the fourth root of 3z over
The fourth root of 3z. Is that right? Divided by the fourth root of 3z is another name for 1. Because, all right, the fourth root of 27z cubed times the fourth root of 3z is, now think of the number 27 as 3 cubed, okay? 3 cubed times 3 is what? 3 to the fourth. And the fourth root of 3 to the fourth is 3. And that's exactly what you want. There's 3. Now the fourth root of, here we have z cubed times the fourth root of z is what? The fourth root of z to the fourth. And the fourth root of z to the fourth is z. All right, and there you have simplified your denominator. You rationalized your denominator. Okay? Now whatever is left in the numerator is, well, whatever we have there. There's a 2xy times, now here we have the fourth root of x times the fourth root of 3z, and that's equal to what? Anyone? This is what? The fourth root of 3xz. Okay? And now that is the most simple name for this expression here. Okay? Let's call this one number 1, and let's look at 1 or 2 other examples. Well, suppose we had a situation in which we had the sixth root of, now let me take an expression such as x minus 3 all to the sixth power. And going right back to the definition, how may we write this? The sixth root of x minus 3 all to the sixth power, Bob says, is x minus 3. Now, as soon as we write x minus 3, we have to be careful about the variable x. What conclusion must we come to about x here? What must we say? Where x is what? Where x is what? Is greater than or what? Or equal to, careful now, not 0. If x were 0, 0 minus 3 is negative 3, and here is a positive number is equal to a negative number, and that wouldn't be a correct statement. Is that right? And so, in fact, our definition tells us that this number here must be non-negative. So x must be greater than or equal to 3. Okay. Now, what's another way in which we can say this without having to put in that restriction? What else may we say? And we may write here what? In terms of, what may we say? Ken?
The absolute value of x minus 3.
The absolute value of x minus 3 will guarantee this number to be positive. Is that right? Okay. And I think then that would be our conclusion for this statement right here. Well, let's look at a third example, and I think that's all that we need to do for today. Suppose we had the seventh root of some expression, such as suppose I took a negative a to the 8th power, the opposite of a to the 8th power, b to the 14th, c to the 21st, okay? Now, again, the seventh root of a negative a to the 8th. Now, you may think of this as what? Negative a to the 7th times a. Is that right? Or in fact, you may also think of it as a to the 7th times the opposite of a. So let's now take the dash symbol outside the radical, if we will, okay? So what's another name for the 7th root of negative a to the 7th is what? Is the opposite of a. Is that right? Negative a, or the opposite of a. Now we still have left under the radical what? A, all right? And what then is the 7th root of b to the 14th is b squared, and the 7th root of c to the 21st power is c cubed times, and we still have left what? The 7th root of what? Of a. And that then is the most simple name for this expression right here. Okay? Let me give you your assignment for next time, and I think